Well, welcome. I'm JJ. Let's go ahead and tackle an example problem. So in this one, we have a 3,000 pound cylinder is supported as shown by cable A, B, and C. And we're going to try to figure out what's the tension all of those cables in here. We're just going to jump in and get going with that. So our very first thing we want to do is say, if I'm doing this, I have coordinates for everything labeled in here. So I probably want to use position vectors. If I can get my position vectors, I can get my unit vectors and force vectors. Once I have my force vectors, I can sum everything up and set it equal to 0 and solve for my unknowns. So to do that though, let's let's write out just super clearly what are my coordinates. So my first step is clearly document what are the coordinates. What are the coordinates that we are taking a look at in here? So I'm going to need coordinates for A, B, C. The center of our ring here is just the origin for us. So it's 0, 0, 0. We don't really need it. But let's get the coordinates for everything in here. So point A is located at, we're going in our y direction 4 feet. That's the x. In the x direction, we're going 4 feet. The y -3. The z direction, we're going up 6. So we are at 4, -3, 6. And our units here are feet. Our little tick mark there means feet. We just need to repeat that for our other coordinates. Let's do this for B. Point B is at, we go backwards 4 in the x, -6 in the y, and up 4. So we'd be at -4, -6, 4. Will be our second point in here. And then finally, we have point C. I'm going to write this down. C, we don't actually know how far out here this is, and it doesn't matter for us. C's coordinates are irrelevant. Coordinates do not matter. We'll talk about why that is as we get to like our unit vector step on everything in here. Unit vector, force vector step for that. But for right now, if we have a cable that goes parallel to an axis, we don't need the coordinates for it. It's kind of the takeaway at this point. But if I have that, I can then come in and say, well, let's start getting, what are my position vectors and their magnitudes. Before we do that though, if I'm trying to get a equilibrium set up, I should draw a free body diagram. So I'm going to skip down here and say my second step on this is just, let's draw a real basic free body diagram. So if we're doing that, we could circle where everything comes together right here. And I'm cutting all 3 of my cables I'm looking for and the one holding up that 3,000 pound weight. In 3D, our free body diagrams can get annoying to try to draw. Just do your best with it, but don't worry if it's terrible. But we should have a 3,000 pound weight going straight down. 3,000 pounds. And then we have, loosely, I'm going to get my other ones in here. I'm not going to worry about getting like my X, Y, Z axes labeled. It's just a good habit to keep drawing free body diagrams. So we're still going to get something drawn in here. But straight to the right, I have cable that goes from the origin to C. Let's call that the force in OC. And that'll be one unknown for us. I also have going up and to the left an FOB, a force in cable that goes from the origin to point B. And then up and more sharply to the left, I have a cable that goes to A. So let's come in and put in one more unknown in here that goes from the origin to A. FOA. We can call that one. I'm going to move that just a little bit. FOA would be my third cable I'm looking for. So the 3 unknowns, if I'm dealing with 3D particle equilibrium, I can sum forces in the X, in the Y, and in the Z directions, which means I really have 3 equations. I can find 3 unknowns. This will be a solvable problem. But let's get those set up because then we can start naming all of our vectors to kind of match this OA, OB, OC nomenclature in here. So my third step is going to be to come in and say, I want to get my position vectors position vectors, and their magnitudes, we know to get a position vector, we want to do the coordinates of the tip minus the coordinates of the tail. For all of these, our cable in our free body diagram, we're starting at the origin and we're pointing out to our other points. So I'd be doing A minus the origin, B minus the origin, C minus the origin. Again, I don't actually need that one, but it'd be the same process in here. Really, we need to get, though, an ROA and an ROB calculated out in here. So ROA, we're looking for a vector that goes from the origin to A, again, matching our force vector in here. ROA would be the coordinates of A minus the coordinates of the origin. Really, if the origin is 0, 0, 0, 4 minus 0, negative 3 minus 0, 6 minus 0, for this problem, it's just going to get us the coordinate of A. So 4I minus 3J plus 6K feet. If we weren't starting at the origin for this, if this was coming from a different point, we wouldn't just be able to take the coordinates of A for that. It's just kind of a fluke thing or a conveniently chosen thing to make this the origin for it. So don't blindly just use the coordinates. We are doing tip minus tail on this. It's just the tail 0. But we can work with that to get what's our magnitude of ROA as well. The magnitude of ROA should be equal to the square root of our x component squared, 4 squared, plus our y component, 3 squared, plus that z component, plus 6 squared, or ijk. This is going to get us that our magnitude, or that distance from the origin to A, is 7.81 feet. So we have one of our two position vectors and its magnitude figured out. Our next step would just be to repeat that for ROB. So for ROB, making sure I'm not writing on my diagram, ROB would be, we're going from the origin to B. So the tip is at B, the tail is the origin. The coordinates of B minus 0, 0, 0 is just the coordinates of B. So our position vector here is negative 4I minus 6J plus 4K feet. And our magnitude of that, the magnitude of ROB, should get us to our square root of our I component squared, 4 squared, plus our J component squared, 6 squared, plus the K component, 4 squared again. Or this is going to get me that this is equal to 8.25 feet. If we've been keeping up with all of our material so far, these aren't terribly difficult steps for us to go through in here. It's easy to make silly sign errors and things like that. But these steps aren't terrible. Our 3D problems we can work with. It starts to become more of an algebra challenge when we actually apply equilibrium into everything. But that is our third step we want to tackle in here. Our fourth step, we can say, we just want to come in and let's combine unit vectors and force vectors into one step in here. Unit vectors and force vectors. We know to get a unit vector, we take the position vector divided by its magnitude. To get a force vector, we take our unit vector and multiply by whatever the force is. We can combine those into one step really easy. To get like an FOA, the force vector that goes from the origin to A, should be our magnitude of FOA. That's going to be an unknown we're actually solving for. FOA times our unit vector, UOA. I don't know that unit vector yet, but let's substitute in just a quick equation for that. This is the same thing as our magnitude of FOA, our force vector. Again, this will be the unknown. That's one of our answers when we can solve for that. That's going to stay as an unknown for a while in here. We multiply by our position vector, ROA, and then divide by the magnitude of our position vector, ROA. And I have these two parts. I can leave this as an unknown in here. Again, when I apply equilibrium, that will fall away from everything. But this is going to get me to our unknown FOA, times our unit vector, or times, and the ROA will be the top, 4I minus 3J plus 6K. And we're dividing that by the magnitude, 7.81. 7.81. We would have force here. We were in pounds for our cylinder, so pounds, distance, feet divided by distance. Those distances cancel. And we just have units of force will be all that's left over here. We'll pull those back in when we actually get our answer. But unit-wise, we're actually checking out for how we should be looking for everything. But our next step, let's actually get that written out. What do we get here? This is our unknown FOA. Again, ultimately what we're looking to solve for, times 0.521I, 0.521I, minus 0.384J, FOA times negative 3 over 7.81, minus 0.384J, and then we have to add in, or plus, 6 divided by 7.81 times our FOA. Look at us, plus 0.768K, plus 0.768K. But that is one of our force vectors in here. We need to repeat that for every other cable in there. So let's get, I'm not going to write out all of the steps in here, but let's get our FOB written out. FOB should be our magnitude of FOB. Let's write this form of it. Our magnitude of FOB times our position vector, ROB, divided by the magnitude of our position vector, divided by the magnitude of ROB. Or this is, again, our unknown FOB times our position vector, ROB, negative 4I minus 6J plus 4K divided by the magnitude, 8.25. Which is going to get us that our force vector here, so I should have a line over that, is that FOB is equal to our magnitude, the unknown I'm going to solve for, FOB, times negative 4 divided by 8.25 would be negative 0.485I, 0.485I, minus 0.728J, plus 4 divided by 8.25 is again 0.485. So plus 0.485K, just evaluating this term in here and getting our decimals written out. That would get me a second force vector. Let's go ahead and get, let's get a weight vector. Our weight in here, we know it's 3,000. If we're trying to get that as a Cartesian vector though, I need an IJ or K on this. This goes straight down in here. If it's going straight down, well, positive K goes up, so our weight is negative, going down. I could really say that my weight as a vector is negative 3,000 pounds in our K direction. Getting that negative because it's pointing down, K because it's entirely in the Z direction. That logic should apply exactly to FOC as well in here. FOC is entirely in the Y direction. It doesn't matter where it's at. Just like it doesn't matter, does this cable, is it 1 inch long? Is it a mile long? Probably neither of those, but it's somewhere in there. The coordinate doesn't matter because it's just straight up and down. I only need the coordinates so I can get to my position vectors and their magnitudes, get a unit vector. I know this goes entirely in the Y. It's just 1J. This was negative 1K. That's it to it. So my FOC as a vector, I could really just get at this point. FOC points in the positive Y direction, So it's just FOCJ equals our unknown magnitude FOC times the J vector. And that's it for us. I have 1, 2, 3, 4 force vectors. One of them's known. 3 of them have an unknown in it. That's okay. We can work with that. But that is our 4th step. Our last step then, we need to apply equilibrium and solve some stuff out for that. I'm going to erase this, and I'm going to pause the video, but just to talk through what I'm doing. I'm going to erase it and just pull in our force vectors up at the top so we have plenty of room to actually do the algebra on this. So we'll hit pause and be right back. All right, so all that I've done there is erased everything we had, so we have plenty of room to apply equilibrium here. And I've rewritten our 1, 2, 3, 4 force vectors that we have. We still have our free body diagram here. Let's go ahead and go with our last step. The last thing we need to do, this is our 5th thing, was getting to this step. So we can say our 6th and final step in here. 6 is just apply equilibrium. Apply equilibrium. And solve. And solve our problem out. So in 2D, when we applied equilibrium, we just summed forces in the x and the y, set our equations equal to 0, and found our unknowns. Really, we're just adding in. We also have k terms, or z directions now. I can add that in, still set it all equal to 0, find my unknowns. So if I'm doing this, I would start out and just go for it. Sometimes we can do one equation, find one unknown immediately. When in doubt, just start making equations though. So I'm going to start by summing my forces in the x direction. If I'm doing that, x correlates to an I component. So I just want to go to all 4 of my force vectors and pull in any I component that I have. So for my first one, I had 0.521 FOA. 0.521 FOA. From the second one, we had minus 0.485 FOB. Minus 0.485 FOB. The weight only has a K component. FOC only has a J component. There's no more X components in here. No more I terms in here. So I can set this equal to 0. As soon as I do that, I can now start rearranging this. I have 2 unknowns in here, 1 equation. I can't solve this out, but let's try to simplify it down. I'm going to move my 0.485 FOB to the other side of the equation and divide through by 0.521. That'll get me an FOA equals statement. FOA equals 0.946 FOB. And that's as far as I can go. Let's call that equation 1. I'm kind of stuck there. So we can move on and do another equation. Let's sum our forces in the y direction. Summing forces in the y. I have y goes with j. So I'm just going to grab all my j terms in here. So negative 0.384 FOA. Negative 0.384 FOA. Minus 0.728 FOB minus 0.728 FOB. The weight only has a K term. FOC is entirely in the J. That means we need to include it here. So plus FOC, and that's it for us. So we can set this equal to 0. Let's go ahead and get an FOC equal statement out for this one. FOC equals, and I'm just moving the 2 negative pieces to the other side to accomplish this. FOC is 0.384 FOB plus 0.728, oh, that's FOA. My bad. FOA plus 0.728 FOB plus 0.728 FOB. I have 1, 2, 3 unknowns in here. This is 2 equations I've set up, but I can't do 3 unknowns, 2 equations. Let's just call that equation 2. We'll have to make one more equation out for this. Our last one we can work with is sum all of our z components. So summing forces in the z direction, I'm going to have in my FOA 0.768 FOA, so 0.768 FOA. In my FOB vector, I have 0.485 FOB, so plus 0.485 FOB. My weight was negative 3,000, so minus 3,000 plus nothing here. It's just a J. So that's everything for us. I can set this one equal to 0. Again, let's go ahead and rearrange this. I'm just going to move the 3,000 to the other side. We get an equation here, 3,000 equals 0.768 FOA, 0.768 FOA, plus 0.485 FOB, plus 0.485 FOB. Two unknowns in here. It's the same, or two of them that I've used before. I really have a third equation, though. 3 equations, 3 unknowns. I can work with this. Really, I have between equation 1 and 3. It's the same, 2 unknowns. I can do 2 equations, 2 unknowns here. Let's start there. I'm going to take that first equation, and I'm going to substitute it into the third one. So I'm doing equation 1. I'm substituting into equation 3. So anytime FOA shows up, I'm going to write 0.946 FOB. So let's just start going through this equation. 3,000, we're rewriting equation 3, equals 0.768 times FOA. But I know FOA is really 0.946 FOB. So we'll make that quick substitution and then keep going with that. Pick back up in equation 3 plus 0.485 FOB. Which all of a sudden, I'm down here to one equation here. I only have FOBs in this. I can multiply these two together and add 0.485. I can solve for FOB. I'm going to get the FOB is equal to 2,476. 2,476 pounds. Would be our first answer for this. And then really it's just substituting back into previous equations. If I have this one found, let's just substitute into equation 1. FOA is equal to 0.946 FOB. 0.946 times FOB, which we just found, 2,476. Which will get us that this is equal to 2,342 FOA equals 2,342 pounds, which is another answer for us. That gets me FOA and FOB. That means I can put both of those in here into equation 2 now, and I'll find FOC out for this. So let's write that one out. FOC, just rewriting this, I'm just substituting in known values now. But FOC should be equal to 0.384, 0.384 times FOA, 2,342. Plus 0.728, 0.728 times FOB, 2,476. 2,476. Will get us FOC. We can solve this out. FOC is equal to 2,702 pounds, which is our final answer for our problem. These 3D equilibrium problems, they take a little bit longer. As you can see, I had to stop and erase everything and then filled up a board again. Go slow and steady with it. No individual step in here is terrible. Also, I would tell you, just be really careful with your algebra in here. It's hard to make an algebra mistake. This can be hard to figure out where an error went wrong if something comes up off. Just go slow and steady. We can do this. But if this was useful for you, hit that like and subscribe button. Let's get you an A with JJ.